All right, in this video, we're going to talk about Chapter 6 of our textbook, um, Introduction to Business Data Mining, and we're going to talk about regression. And tonight we're going to cover ordinary least squares regression, building regression models, and then we're going to talk about multiple regression, which will show us how to do assignment 6. So I'm going to go ahead and share my screen here. And so if we take a look at our studio here, first thing I'm going to do is just load up a couple of these libraries, and I'll give everybody this R script file as a part of the assignment. And so the first thing I'm going to do is just load ggplot and mass here, because those two libraries we're going to use. And I'm going to set this my computer variable just because we use that a lot of times in our screen prints. And then we're going to go ahead and we're going to actually start working on understanding regression. So really what regression is we're trying to establish a correlation between an independent variable, which we'll call X, and an independent variable, which we will call Y. And so in a perfect world, Y is a function of X, which means for any value you have of X, you can predict the value of Y. Now, this isn't really how it works most of the time in the real world. It's generally a little more complex than that. But we're going to start off trying to understand regression and how it works, and specifically how we can work with it inside of our studio by designing a perfect world scenario, right? So the first thing that I'm going to do is I'm just going to create a vector here, and we're just going to set X to 1 through 10, right? So if we take a look here, we've got X values from 1 to 10. And then for my example here, I'm going to set Y equal to X times 2. For your assignment 6, you're going to want to do Y is equal to X times 2 plus 1. That'll be really the big difference, and I'll just kind of prove that you guys are able to walk through and understand this stuff by not using the exact same variable as I use. So, okay, I'm going to set Y equal to X times 2. And because Y is 100% derived from X here, what we're really building is a sort of what I'm calling a perfect data model here, because we'll be able to correlate 100% the relationship between X and Y. So I'm going to go ahead, create this perfect data frame based off of X and Y, and then if we take a look at perfect here, we'll see that we have our X and Y values, and so we can follow along here and see that Y is perfectly a function of 2 times the X value. So now if we want to create a plot to kind of understand this relationship here, we can run this plotting command, and we can see that we've got X and Y plotted here, with X along the bottom, Y along the left edge here. And we can see that we have a sort of perfectly sloped line because we have created these values the way that we have. Now, just a note here, with some of the stuff that we're using, we'll see that some of the values in our regression model can be expressed in scientific notation. If you want to turn scientific notation off, I've got this option set right here where you can turn it off and it won't use scientific notation. Or if you wanted to use scientific notation, which is particularly handy when you have ridiculously small numbers like we will with this particular model, then you can turn it on. Just want you to be aware of this ability to sort of toggle it on and off, because sometimes it can be a little bit annoying when you get scientific notation where you don't necessarily want it. So next thing we're going to do is we're going to actually create a regression model and see what we get here, right? So what we have is we're just setting a seed, so this stuff is reproducible. We've got a variable perfect mod that we're going to set equal to using the LM function in R, which allows us to build a regression model. And we're basically saying here that the input is, hey, we want to find the relationship between Y and X, and we're going to use this perfect data frame that we just created, right? So, all right, I'm going to run this thing, and then we're going to take, using the summary function, take a look at the results that were produced right here. And the very first thing you're going to notice is, hey, we get this warning, and it says, hey, you got a perfect fit, which is kind of weird, right? That doesn't really happen. So, you know, warning, you know, this might be bullshit is basically what that means. But we know that because we have created a perfect correlation between Y and X. So if we take a look at the values that we come up with here, if you've read chapter 6 in the book, the author talks about how we can calculate Y based off of the creating a regression model. And the two values that we end up with are this intercept value and then this coefficient for X, right? And so in the book, he says that, hey, Y is equal to the you know, the intercept plus X times its coefficient, right? So that's the basic formula that we end up with to calculate Y based on our regression model here, right? And you might notice this kind of looks similar to the slope of a line if you remember geometry at all. And then obviously this continues out for each value of X, and at the very end it has the error term, which is a kind of a reflection of how accurate our regression model is, right? So, all right, let's take a look here. The first thing that we see is this intercept is 2.247, and then we see this E negative 15, right? So in R, what that means is we're using scientific notation, and that number is equal to 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 2247. That's the decimal that is expressed by that number, right? So our intercept term for all, and really all that means is where Y intercepts the origin, or when X is equal to 0, is essentially 0, which is exactly what we would expect, right? Because Y is a function of X, and so we would expect that when X is 0, Y would be 0 as well. And then the other thing that we see is this X coefficient 2, and then we have a scientific notation of E to the 0 power, which is 1, so 2, right? And so what that gives us is a formula that we can use to predict our value of Y. And we can actually pull these coefficients out of our model using this coefficient function. We can see, hey, there's the intercept, and then here's the coefficient for X, right? And so then if we want to build our own prediction function, we could do that, which is what I've done right here. And I'm saying, hey, this you know, pred Y function, we're going to set this equal to our intercept, and I can just copy this out in its scientific notation form and paste it in here. So I can say it's our intercept plus X times the X coefficient, right? And so if I just copy these two values out here, leaving them in scientific notation, that's fine. I can create that function, and then I can use that function to actually create, or I can use that function to predict the value of X, right? So if we take a look at the X values we already have, which we know to be 1 through 10, we would expect our function to barf out 2 through 20, right? And so if we do that, we can see here in scientific notation, that's what it's doing. But this is kind of one of those cases where it's like, ugh, that's hard to read, right? So if I go back to these options here, I can turn the scientific notation off, and we can rerun this function here, and we can see, hey, we've got a vector, it's 2 through 20, exactly what we would expect based on the values that we put in there. Now, the other thing we can see is, hey, our model has these inside of them as well. So if we take a look at this, we can pull out the fitted values, or the, kind of the predicted values of X from our regression model, and we'll see that they are also 2 through 20, which is exactly what we would think they'd be. So the next thing that we can do here is we can actually use this model to predict our values. Now, this isn't really going to be a big mystery to us because we know exactly what to expect, but in the case where we're using a regression model for a sort of more complex data set where we don't know, we don't have a pure correlation, then this would be able to produce results that we wouldn't be able to just sort of infer from the fact that we know what the relationship is here. So, all right, I'm going to create a new set of X values, and we're going to set these equal to 11 through 20. We see here our vector is a set of values from 11 to 20. And then we're going to create a new vector of Y values, and we're going to use our function. So we're using sapply to apply this function to every value inside of this X new vector. And there's our prediction Y function. So we'll go ahead and execute that. And then when we take a look here, what we're saying is, hey, we predict that, for a value of X, we're going to get a value of Y equal to 22. And so on and so forth, right? And so then we can create a data frame from these two new X and Y values that we have. And you can see that I'm actually going to set X equal to X new and Y equal to Y new. And that's just so that my column names will be named X and Y in this new data frame. And so we're going to call this data frame perfect prediction here. And if we take a look at this now, we have a set of values of our predicted values for Y for our values of X, right? Now, if we wanted to visualize these results, we can actually use this LM method as a part of our plot function. And you can see right here, I've got a plot that I'm calling a relationship between X and Y, and then I'm actually going to put a line on it that shows the expected values of Y. And because we know there's sort of a perfect correlation between these two, we would expect this line to follow along directly with the points that we have here. So I'm going to go ahead and execute this. And we'll see that it has indeed drawn a line that goes exactly through all of our points, because all of our points are 100% predictable. So one of the things we'll see when we get to a non-perfect model is this idea of residuals, right? So residuals are the differences between the predicted value of Y, in this case, and the actual value. And if we take a look at the residuals for our model, you can see I shut off the scientific notation. These are really, 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 really small numbers, right? Which basically means, hey, there's a about 1,000% chance that that this thing is 100% accurate here. So, all right, we can actually take a look at those residuals and how they are fitted with their predicted values using this, using the plot function. And if we do that, what we would expect to see in a really, really perfectly fitted model like this one is a sort of random distribution about this line, and then we can also see that the variance here is really, really small, right? So this basically says, yeah, this thing is perfectly fitted, which is kind of exactly what we expect, right? Now, we could write our own function, and really the only reason we're writing our own function is because we want to understand kind of how to do the math here, because in my mind that makes it quite a bit easier to understand what's going on with these functions when we use them. So I always try to, when I'm learning something new, I always try to write the math that these functions actually do, so that I make sure I understand what they're doing. And then after I do that, I resort to being lazy and kind of never doing that again, right? And so there is the predict function that we can use with a model that basically says, hey, we would like you to be able to predict the values of our dependent variable based on the independent variable or variables. And then we would like to use that mechanism to just go ahead and predict those. And so here I've got this vector that, or I'm creating a new data frame here, and we're just going to set our values of x equal to 11 and 20, 11 through 20, like we just did. I'm going to go ahead and execute this. I've produced a new data frame here, which we can see has the x values inside of it, and then I can use the predict function to go ahead and predict the value of y based on the values of x that are inside of this data frame that I'm supplying to the function. So I'll go ahead and execute that, and you can see that we have our predicted values of y right here. And if we wanted to actually write these into our data frame, we could do that. We could simply say, you know, x new to column y is equal to the results of our predict function. And I believe that'll just pump those right in there. Let's go ahead and execute that. And now if we took a look at our x new data frame, we've persisted our predicted values right into that data frame. Now the other thing we can do is we can actually create our prediction and have a confidence interval around it too, right? So we can go ahead, if we take a look at what happens when we use the predict function and use this interval prediction, we'll run that. And you can see that we get our predicted values of y running down this fit column, and then the lower and upper bounds of the values based on I believe the standard error, right? So here we don't have any error, so our lower and upper bounds conform perfectly with the values that we're predicting. But we'll see when we have something that's a little more uncertain, there's a range here that develops, right? So then with our using the confidence option here, we get lower and upper bounds based on a 95% confidence interval here. So all right, I'm gonna run both of those into these variables, and then we're gonna plot this, and we'll see in a minute how this will look a little different when we have a non-perfect model. So what we've actually got here is a line for our predicted values, and there's actually, I believe, 5 lines drawn on this plot, but because they are all, you know, because this model is a perfect correlation, they're all right on top of each other. What we'll see in a minute is what actually happens when we have something that is less than 100% correlated. All right, so there we produced, we went through and we built a regression model that is based on something that we know exactly what the values are and should be, and we're able to sort of look at what the model does and understand why it's doing it, because it's pretty simple to predict the numbers that are going to come out, because we set y as a function of x. So for the second example here, what we're going to do is we're actually going to create random sample of 10 numbers between 1 and 10. And so if we run this and we take a look at the vector we've created here, we just sort of randomly selected numbers between 1 and 10, and then we're going to set our y2 variable equal to our original y values plus a random number, right? And what we're doing here is we're introducing some variability into our model, because we understand that this random set of numbers is not something that should be predicted by our regression model, and so we would expect to see a correlation of less than 100% between our model or between our x and y variables at this point. So all right, let's we're going to create a new data frame. We're going to use our same x values. We're going to use our new y2 values that we have here. And you can see I've got this set to y2. I could just say, you know, y is equal to y2, so I could easily kind of reuse my code over and over. And then instead of having to put this y2 in here, I can just leave it x and y. And then this function that scales the y-axis, I can just leave y, and that way I can reuse this for multiple data sets. Anyways, I'm going to go ahead and create my not perfect data frame, and if we take a look at this, we've got x and y values, which we know some portion of y should be predictable, because we know that our original y value was equal to x squared, but then we're throwing a random number on top of that value. So again, we shouldn't expect this to be 100% predictable value anymore. So if we create a plot of what we've generated here, we could see that our numbers are a little more distributed, right? And so we're seeing values that don't sort of follow a perfectly sloped line. Now, what we should have seen here is I would have expected that this max y would have given us a value outside, or would have given us our max y value here. Let's just take another look at our not perfect here. Our max value, oh, this is probably picking up on the variable y that we had earlier. What we really do want to put here is either y2, or we want to make sure that this references the y column inside of our data frame. So now if we rerun this, we should see that our scale now builds to the actual maximum value of y the way we'd expect. So if you remember, in our first plot, we had a perfectly aligned set of points, and we were able to draw a line right through them. But now we can see that these lines are a little more randomly distributed, but they still seem to be following a pattern, which is exactly what we'd expect. So now we're gonna build a model off of this, and you can see here, setting a seed. We're going to call this our not perfect model. We're using our LLM function again, and then we'll take a look at the results that we get from that model. So I've run that, and now you can see before, when we ran the model, there's a sort of measure of how accurate our model is here, this multiple R squared, and this is basically varies from 0 to 1, with 0 being there's no correlation between the variables that we've used in the model, and 1 being equal to there's 100% correlation, right? And then the you know, we've got stuff like the standard error, which we'll talk about a little bit here as well. But then you got the p-value, which is kind of a reflection of how likely it is that there's no relationship between our variables, and we can see that probability is very low in our original model. So now if we come down here and take a look at the model that we just ran, we can see that we still have a pretty high number here, right? We're saying basically that there's 81% correlation between these two variables, and but now we've got a little bit more error in our model, and we could see that our p-values come up as well, right? So essentially what we're saying here at this point is, hey, there's definitely some correlation between these, but it's not as strong as it was before, which is exactly what we would expect, right? Because we have put a random number on top of the function that we were using for y. But we can still build another predictive function if we wanted to off of this, and we can just come right in here. We could see that our intercept value is equal to this number, so we know if we are building a function, it's going to be equal to the intercept plus x times its coefficient. And then if we build this new prediction y function, we can actually use it to tell us what we would expect our values to be, right? And then we can also, if you remember, we can get the fitted values from our model. So our model says our predicted values of y for our given values of x, 1 through 10, are these values that you see underneath each number. So if we take a look at our predictive function, we could see that the numbers that we created are very close to these as well. They're just rounded off a couple of digits before the other one. So this gives us a pretty good sense that we understand the math that's going on here, right? With how y is being predicted from the values of x. So now we can go ahead and do some plotting of this, right? So if we had a new set of x values, 11 to 20, we could predict what we thought those values were going to be using our custom function, right? And this is what we predict them to be. Or we can, we'll see, use a predict function as well. So now this time, again, we're gonna plot this, but we'll see a little bit of a different scenario this time. So now we can see that our line is not perfectly fitted to our data points, which is a lot more like we'd expect in the real world, right? But we could still see that, hey, this seems like a pretty decent model because we've got this kind of random distribution about the line. And that we could see pretty clearly that the shape of the data follows along the slope of the line that we're plotting here. So, okay, now we can take again a look at how well this fits. We see this time that our residuals are significantly larger, but we have a still random distribution about this line, which is what we would expect if our model is working correctly. So we could take a look at the actual residuals that are produced by our model. If you remember, we can just come and say, hey, let me see the residuals from our model. And so if we run those, we can see before that we actually have some, differences this time that are quite a bit larger, at least compared to, if you remember, we had things that were 10 and 15 points right of the decimal point as our residuals before, which is the difference. The residual is the difference between the actual value and the predicted value. But in this case, we're seeing these numbers are a little bit larger because obviously we know that y is not 100% predicted by x now. So to make sure that we understand what the residuals are, we can actually calculate them if we want to as well, right? So the residuals are equal to the difference between, oh, I see, I just misspelled that there. Difference between the predicted and actual value. So I've got this my residual variable that I've set up here, and we can see we've got our fitted values, and we're just going to subtract those from y2, which, if you remember, was our set of Y values that we created. So we'll just run the Y2 so remember what these are. Those are the values that were created. And now if we look at the fitted values, these would be the expected values of Y based on our regression model. We can see that these are clearly different, and then the difference is going to be the residual, right? So now if we run these residuals, we will see that these are the same basic numbers that we saw up here. Now you can see the signs are different, but in the calculations that we do, it doesn't matter, because the first thing that we do is we actually end up squaring these when we use these for calculations such as the R squared value, right? So the other thing I want you guys to do is actually calculate R squared on your own, so you understand what's going on with the math here. And the way that we get to that number is the first thing that we do is we square these residuals, right? So I can take my residual, I could square all the values. We can see that makes everything a positive number. And then what we end up doing is we end up summing these squares up, right? So if I run this, you can see that number equals the sum of all the squared errors. And so we could set a variable, which I'm calling my sum of squared errors, right? And so then the next thing we need to do, and this is all in the textbook as well, the author goes through this and explains how R squared is calculated. R squared is actually equal to the total sum of squares, which is the next thing that we're going to calculate, minus the sum of squared errors, which is the value that we just calculated, divided by the sum of squares. So the sum of squares is the difference between Y and its own mean, and then it's all squared up as well. So you can see here we've got our Y values, and we're calculating the difference between the mean of our Y values, and then we're squaring that. So if we took a look at these individually, we'll see that the mean of Y is this 16.5 or 16.5. We take a look at this vector Y2. These are our original Y values that we're using in this model. Then we're doing a subtraction. We're squaring that whole mess, and then we're summing it up. And ultimately, this will be our total sum of squares, right? So I'm going to run that, and we can see that now we have this number that is our total sum of squares. So now, just to calculate R squared, we use that formula that's in the textbook. Got our total sum of squares minus our sum of squared errors divided by our total sum of squares. So if we calculate this whole thing up, run that, and take a look at this value, we can see that we've calculated it to be 0.813. And then if we take a look at the summary of our model, we should see a very similar number, which we see right here, this multiple R squared. So the purpose of that is just to kind of help you understand how the math works, because this stuff can be kind of mysterious at first, and if you just jump in here and start cranking these things out, it becomes kind of difficult to understand what's going on. But really what we're doing here is math that's pretty easy to calculate on, you know, predictable stuff. And obviously it gets tedious when you get to really huge data sets, and obviously you wouldn't want to go through and do this manually like we've just done it for, say, you know, tens of thousands of values. But you certainly could use the stuff that's available to you inside of R. But, you know, before you get to using, you know, those type of data sets, it's important to understand what's going on so that you can then use the built-in functions to do this type of, you know, tedious work for you. And then you have an understanding of what's actually going on here. So, all right, now we're going to use our predict function again. we're going to go ahead and run that for our new values of X and Y. We could see these predicted values here from the predict function. We can also see our manually predicted values, and we can see these numbers are the same except for the significant digits. So that proves to us that we understand the math that's going on. And then we can use our function to predict the new values. So we're going to have these values 11 through 20. Here's our prediction based on the manual function that we created. We'll create a new data frame here. We'll pass it to our predict using the model that we just created, and we would expect that it would produce the same predicted values of Y as we saw from our function. And we can see again that these numbers are same, but for the number of significant digits here. So all right, we'll do the same thing with our intervals again. And this time we would expect to not see a bunch of lines on top of each other, but we would expect to see these lines spread out here. So now if we run it, we can see that indeed that is what happened. So if you want to understand what these numbers are equal to, there's a couple of different things you can do. One, you can just kind of take a look. We can see here if we run this without running it into the variable, that our lower and upper bounds are no longer perfectly correlated with our fitted values. And then same thing here with our confidence as well. So that's what these are the lower bounds and upper bounds respectively, and then this here is our predicted value Y. And if you wanted to read up more about what you're seeing here, you can always use question mark and predict, and you can look at the documentation for this function and read up about exactly the things that are kind of going on here. So all right. We've gone through and we've shown, hey, we want to kind of understand this regression math a little bit before we dive into any real data. And so the final example that we'll do here is we're going to create something that's has no correlation and see what happens to our model, right? So we're going to use, again, X 1 through 10, and this time Y is just going to be a totally random number. So we're going to pick out 10 values between 1 and 100 randomly sampled. So now if we take a look at these values, we've got 1 through 10 for X. We've got a set of 10 numbers randomly between 1 and 100. We would expect that our model has, pretty low confidence at this point, right? And so we're gonna put this into another data frame. We'll call this one dog poo because we know that these numbers don't have much to do with each other. We will go ahead and plot these so that we can see what it looks like. And we get a plot that looks pretty randomly distributed, right? And so now we can build a regression model off of this. And now we take a look at this thing, and now we're seeing quite a difference, right? Now the correlation between these two values is very low, and the probability that this doesn't have anything, one variable has nothing to do with the other is very high, right? And we expect that to be the case because, in fact, these variables have nothing to do with each other, right? One is a set of 10 numbers and that are just generated 1 through 10. The other is a random set of numbers from random set of 10 numbers between 1 and 100. There's no correlation between X and Y here, right? And so again, we can visualize this with the line. We can see here that this looks like a randomly distributed set of numbers, and we can, fit that again Now we're not seeing that random distribution about the line like we would expect, but this sort of odd shape that would suggest that we have something wrong with our model. And so now we've gone through and seen, like, okay, here's what a regression model looks like, where we indeed have nothing, no correlation between the numbers. So obviously there is a huge ton of additional information that goes into this, right? But we're just trying to get a sort of handle on the mechanics of how this stuff works. And so we're not going to dive way down into it, but what I want you to understand is, for any of these functions that you use inside of R, you should be able to kind of look at how the math is done and be able to replicate it for simple examples, so you make sure that you understand what this thing is doing. You should be able to produce the numbers that you see being produced by these models. And then after you feel like you have a good handle on it, then you can dive in and really use these things against larger data sets and feel confident in understanding what is going on here. So now what we're going to do is we're actually going to touch kind of a real, or semi-real world example. And there's a set of data included inside of R called chicken weight, which is just some study that was done on chickens over time with a particular diet, and how their weight sort of correlated with that. So if we took a look at this data set here, we'd see we've got weight, we've got a time period, I want to say these were weeks, and then we've got a chick number and the particular diet that we were on, or they were on. For our purposes, and if we take a look at this, right, we can get some of the statistics on our data set here. Essentially, here's the basic structure of it, and we can do a summary on this, and we can see that, okay, here's the distribution of weights and time, the number of chicks, and the different diets. So we could see clearly here that there were 4 different diets. And for what we're doing here, we're not really going to concern ourselves with that, although you could probably certainly use this data set to do some interesting regression modeling. But we're just going to pull a set of data out of this thing where we say, hey, give us all the chick weights for the chicks that were on we're on diet 1, and then we'll just take the first 2 columns of data, right? So, all right. We'll run that. We have a new data frame here. If we see, we've got this new chick data frame we just created or subsetted. We've got weight and time for the chicks that were fed this particular diet, right? And so we could do a summary on this again if we wanted to. Seeing that, hey, we got 2 variables and here's their distribution, right? So, all right, now we're gonna plot this, just kind of get a look at the data that we have, and we can see that we have these varying chick weights over our various time periods, right? And we could see, just looking at the shape of this, it kind of looks like there's a general slope upwards of the data over time. So it seems like weight is kind of tied to the amount of time that goes by. And intuitively, in the real world, that makes sense, right? If you have brand new chickens and you feed them, you would expect them to grow. And then you would also expect that there's going to be some variance in the rate at which they grow, because that's just kind of how things work with the animal kingdom, right? So, all right, we're going to go ahead and create a model off of this. And we can see here that we've got this R squared here, which is still, pretty significant. Seems to suggest that that there's a pretty strong relationship between these 2 variables, and that isn't very likely that there's no relationship between them. So now we can use this model to actually predict the weight on off into the future, right? First, we'll take a look. We'll go ahead and plot this with a line. You can see that the line kind of follows along and kind of looks like it makes a lot of sense, really, when you look at it, right? There's a distribution of weights, on either side of this line, and with a generally increasing slope over time, which is exactly what we thought we'd expect from this. If we plot the residuals, we see a distribution about that as well, so that makes sense to us, and we can actually take a look at our coefficients here from our model, right? So we could see we've got our intercept, and then essentially we would expect our weight to be equal to this 30.93 blah 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 plus time times this 6.84 coefficient, right? That's the function that we would expect to predict the weight of our chicks going forward, right? So now if we look back at the data that we had inside of our new chick data, you can see that the max for our time was 21, and we're actually going to create we're actually going to generate some more time data and attempt to predict weight based on that and the model that we just built. So over here, I'm going to use predict on our chicken model. So we're going to go ahead and predict what we think the values are going to be. We're going to create a new data frame here where we extend out, I think, 9 weeks into the future here, 8 weeks into the future. So there's our new time values, and now we want to predict weight using our model that we just created, right? So we're going to go ahead and plug that stuff into our predict function. There's our predicted weight values based on our time values, and now we can actually go ahead and take a look at this over time. So now what we will do is same thing we did before. We will plot this thing, and then we can see that here's the value that we would expect to happen with weight over time. And then the other thing that probably would not be predicted by the data that we have in this model is we'd expect at some point for this to tail off, right? Chickens don't grow forever. Eventually they kind of get to a adult weight and have a much less sort of predictable weight as it's associated with time, and we don't necessarily have that data inside of here. So that's sort of something you would need to think about if you're using this to predict out over time. But based on the data that we have, here's what we would predict the weight growth to be out into the future, right? And if we wanted to, we could actually kind of combine this stuff together, and we could take our original data and combine it with our predicted data. So if let's just scroll down here a little bit. I think I got a spot. Yeah, here's a function that we can use to put those two data frames together. So we'll scroll back up here, and we can call this, we'll call our new data frame, we'll call this chick actual and predicted, right? And then we're going to combine our two data sets together. So we'll come up here and we will get our new chick data, and we're going to make that part of our new data frame that we're going to create. And then we're also going to add in our new data here, right? So if we take a look at this, we could say there's our predicted values. We actually want to put we know we have time and weight, right? So if we take a look at our new chick data, we see that we have weight and time in here. And so we want to push our predicted weight data into our data frame. So we will create a new column called weight, and we will put our predicted value into that. So we'll go ahead and run that. And now if we took a look at new, we would say that we have our time and our predicted weight, and then we could actually push these two things together and plot this, right? And so now, and we'll see this again some more in a minute, I should be able to actually push those two values together. And now we have a data frame that has both our actual and our predicted values in it. We could graph all of those too. We're going to do that here a little bit lower as we keep going along here. So all right, the next thing we can do is multiple regression, right? And so with this, we're going to put some additional libraries in here. I've already installed them, but we've got the scatterplot 3D and this RGL package. I'm going to make sure that these two libraries are available to me. And now, and you can see I'm getting a little warning here that was built under a different version I'm running. That's fine. And now, instead of two independent variables, we're going to create, or instead of using one independent variable and one dependent variable as we did above with our regression, we're going to do multiple regression. We're going to have multiple independent variables and one independent variable. So again, we're going to run X. We're going to set it to values 1 through 10. We are going to make y a function of x again, so it's going to be x squared. We're going to create a little function for this. Then we're going to set y equal to the x values. And so now if we take a look at x and we take a look at y, we can see we've got y has been set to x squared instead of x times 2. And then we're actually going to create another function which will produce z, which we're going to have be our dependent variable. So this time x and y are going to be the independent variables, and z is going to be the dependent variable. So we'll create a function, and all this function says is hey, we're going to pass in x and y, and we're going to pass back the values of those the square root of those two variables added together. So then we'll go ahead and run this, and now we have this value z, which is, we know again, a function of our two variables. So we would expect these to be very highly correlated, because we know they are, because we just created them that way, right? These aren't sort of real world pieces of data. And then I'm not going to use this outer function. We could actually plot this in a 3D fashion on a plane, but we're not going to worry about that for now. So I'm going to go ahead. If you see this code in here, just go ahead and comment it out, because we're not going to use that. All right, so now we're going to create a data frame based off of these values, right, called z-perfect. So I'll go ahead and run that. And now we can see that we've got 3 values now. We've got x, we've got y, and we've got z, which we know is a function of these two values, right? And then we also know that y is a function of x, but for these purposes, we'll ignore that. We're going to create a model based on this now, and we're going to say, hey, this time z, we want to see the correlation between these z and these two dependent variables, or independent variables, excuse me. I'll run this. And now we can see again, hey, These appear to be darn near perfect, which is exactly what we would expect. And there's a very low probability that these things are not related to each other. And then we are given this time an intercept, and then we have a function that is x times its coefficient plus y times its coefficient. And so if we wanted to write our own prediction function at this point, we would say, hey, it's going to be equal to this intercept, 68722, which I have over here, plus y times its coefficient, which you can see I have here. I'm sorry, x times its coefficient, plus y times its coefficient, which I have here as well. So then we could run that, and we would have a function that should be able to produce the value of z based on the values of x and y. And if we were to run that, we would see that it cranks out these values, these expected values of z. And if we look up here, we've got 2. Yep, that's pretty darn close. And 3, I mean, these, you know, values are within, you know, tenths of each other. And really is exactly what we, you know, expect to be able to do. So, all right, then we can take a look at the fitted values. We can take a look at the fitted values that come out of our model. You can see that we're calculating pretty much exactly the same numbers that are cranking out of there. We can also, again, use our predict function, and we can say, hey, based on x and y, we would like you to be able to predict z. So I can run this, and we can see that it'll crank out, again, the predicted models, or the predicted values of z based on x and y values. So now we can create a new vector of values. All right, so we've got x2 and y2. X is just going to be 11 through 20, which is what we've been doing all along here. Y, we're going to use our same y function where we are essentially passing in our x values and squaring them to set our y values. And then we're going to create a new data frame based off of these values. And you can see that I'm setting x equal to x2 and y equal to y2. If we run this thing, we then see we have a new data frame. It's x and y, values of 11 through 20 for x, the squared values of x in the y column. And then what we want to do is be able to predict z based on those values. So here we have our predict function, and we can actually crank this into a new column called z. I'm going to go ahead and do that. And so we'll run this, and now if we were to take a look at our xy new data frame, we'll see that we have our predicted z values based on the values of x and y. And now, if we can do what we were talking about above and actually put these two data sets together. So we have our original values of x, y, and z, and then we have our new values where we are predicting the value of z based on our x and y inputs. We can concatenate these two data frames together, and then we will have created a data frame that has all of these values together. And this is really, you know, gets into the sort of, you know, predictive analytics, right? Or what people want to do with this type of data a lot of times. You want to take a look at kind of what's happened and make a prediction for the future, and then make some decision based on that prediction, right? So here, these first 10 values were essentially our training set. And then, you know, without checking how this performs against another data set, we're going to go ahead and just say, hey, this thing must be awesome. So we'll just go ahead and predict the future with it, right? Now, this isn't the way you do it in the real world. You would actually test this against another data set. to see if your training data set was actually working as well as you thought it would. But here we're just kind of focused on the mechanics of how this stuff works and seeing that we can put all this stuff together. And then obviously we can plot all of that now. And we're going to use in this case, a 3D graph, right? Because before we just had X and Y values. We're pretty familiar with how that looks. We have an X and a Y axis. When we have 3 variables, you know, visualizations start to get a little more difficult. So here we're going to use a 3D scatter plot, and you can see that we have plotted our y-axis here, which varies between 0 and 100, and that's what we would expect based on our values. We have our x-axis, which varies between 1 and 20, which we can see here, makes sense to us. And then we have our z-values, which are really just height here, basically varying between 2 and 23. And you can see here we have a scale from 0 to 25. And then we've plotted these along the X, Y, and Z axes. So you can see that we are kind of gaining height as we advance along our X axis. And we know that we're advancing along our Y axis at the same time because Y is a squared function of X. So there's a way for us to sort of produce a 3D graph or a 3D visualization with extra variables here. And so visualization gets more and more challenging as you expand beyond 3 dimensions, but there's a lot of sort of interesting stuff out there in the world for you know, accomplishing that stuff. So all right, we've taken and built a model off of this time using 2 independent variables to predict the value, 1 dependent variable. The other thing we want to explore is just some different stuff that we can do with graphing here. So if we take a look, I've got this graph, just this point graph, where we are taking our original values for X 1 through 10, and instead of having those drop lines, we're just plotting the points in space here. We can also do the drop line graph like we just did, which gives us a real sense for where we're hitting our X and Y axes in conjunction with our Z values. And then we can actually, we can also draw a line, a continuous line through space that way as well. And then the one thing you'll notice here is there's actually an angle value in here. So we can sort of affect the rotation of this particular visualization. So if I take one of the values out there, we'll see that this thing sort of spins around. And this is sort of a trial and error thing to get kind of the best looking value or the best looking visualization. You can see as you change this angle, it changes the perspective on the visualization. And I think I kind of settled in and thought that, you know, 125 looked best, but you can see we can try all sorts of different values and you know, get a different view of this thing, which may help to sort of you know, get a sense of the shape of the data, because obviously it gets a little more difficult when you're going across 3 dimensions but still rendering in 2, right? And then we can always set this back to our original angle, which I thought was the best, but you guys can pick a different one if you want to. And so I think that gets us through almost everything I'm asking you to do inside of the assignment from a plotting and calculation perspective, except for this last graph here. We can also crank out what's a 3D rotatable graph, which will actually pull up a separate window and give us a graph that we can actually interact with and rotate around. So if I run that, let me drag this back onto our screen here. See, that produces a 3D graph that we can blow out a little bit. And then this one is kind of interesting because we can actually move it around, right? And so this gives us a way to look at this visualization, sort of all sorts of different angles, and really get a sense of what's going on with this line in our 3 dimensions. So yet another way to visualize your data and get a better sense of its shape and distribution. And there's other things that we can do, plotting planes and things like that with these 3D graphs that are pretty interesting, but not necessarily a part of this assignment. I may actually have one over here in another. Yeah, I think I do right here. So you can see if we run this one, let's see if this will work. Nope, I think I gotta fit this thing. Let me try running all of that. I must have went and broke it in the meantime. Oh, I see the problem. So okay, we can go ahead and create this 3D graph with a plane where we're using we're actually calculating values all across X and Y and Z here, and you can see that creates a pretty interesting visualization. We can also crank this out, do some shading and all that type of stuff with it too. And you can adjust the angles on these two and get a different view of these. So just be aware that there's a lot of interesting stuff you can do depending on the sort of complexity of the data that you're trying to visualize, that can sort of give you a greater insight into what's going on. But we're not going to mess around with that for this particular assignment. I just wanted you to be aware of it. So all right, that gets us through everything we need to know for assignment 6. We have basically followed along with the textbook's definition of regression and how it's calculated. We've gone into R and RStudio here. We've worked through a simple 100% predictable example where y is a perfect function of x. We've seen what the regression model does with that. And then we have worked through and introduced some variability into our model and seen how our models react to that. And then ultimately, we looked at some real world data where we had some chick weights, and we created a value or a model based on that, and did some prediction as well. So, at this point, you ought to be comfortable with, doing regression and multiple regression inside of R, and being able to use various plotting functions to visualize those results, and also be able to predict values based on your models. So that gets us through, or that covers what we're going to cover with chapter 6. There's more in there, and I encourage you to read about it. And if you want to figure out how to do some of this additional stuff inside of R, then hopefully this will give you a a feeling of confidence that you can do that after you figured out how to do regression, multiple regression. The next thing that we're going to do is actually going to be in chapter 8, and that'll lead to our 7th assignment. And in chapter 8, we're going to get into decision tree algorithms, right, and how we can crank those out in R as well. And I know the textbook references a number of commercial products for doing these type of things, and obviously those products cost money for a reason. They're very convenient and can do lots of good stuff, but we're going to stay inside of R and in the open source world, and continue to learn how to do that in these type of operations inside of R and RStudio. So, all right, any questions? The best thing you can do is reach out to me on Skype. This is the best way to get a hold of me. Otherwise, I will try and catch up on email and see if anybody's having some problems as well. But if you need immediate help, please reach out on Skype, and I will be happy to help you as time and our schedules allow. All right, until next time, good luck.